Hi there, let's take a look at some properties of logarithms in this video. Now, logarithms are often confusing because we have a misunderstanding of the notation. When we take a look at the equation 2 to the 3 equals 8, it's often mistakenly read as 2 to the third power or 2 to the power 3 equals 8. But in fact, the third power of 2 is 8. 8 is the power, 3 is the exponent, and 2 is the base. So with that in mind, we want to make sure that we are using this upgraded and better quality notation that a base raised to an exponent is equal to the answer, or power. We can convert that exponential form, which gives us a base of b, an exponent of p, and isolates for the power of p, to the logarithmic form that says logarithm base b of the power p is equal to the exponent x. So indeed, this conversion is the first property that we talk about, the change from exponential to logarithmic forms. Now, we have all of the logarithm laws for the general case as well as for the special case, which is base e, and e is the natural number approximately 2.718. Indeed, these properties of logarithms work for any acceptable base, which is between 0 and 1 for exponential decay, or between 1 and infinity for exponential growth. So here's just a look at some special logarithms. I'm not going to go through them in great detail because the logarithms can always be converted back into the exponential form. And you might think of the exponential form as your first language and the logarithmic form as your second language. So as long as you know that b to the 1 is equal to b, then you understand that log base b of b is equal to 1 by applying this change of exponential to logarithmic form. Similarly, log base b of 1 is equal to 0 because b to the exponent of 0 equals 1. So just always go back and convert your logarithmic equation into an exponential version, and that will probably make more sense to you. Now, this one-to-one property is really saying that for a given base, there is a unique pairing of exponent and power. So what we have here on the left-hand side is an exponent equal to another exponent. And if those two exponents are equal and they have the same base, the one-to-one conclusion is that those powers of m and n must be equal. Now the same thing happens over here. ln or ln is just another way of writing log base e. So each of these properties for base e is just a natural consequence of replacing b with e. And again, e is approximately 2.718. The inverse property is a property that says log base b and b to the cancel, leaving us with stuff equal to stuff. And it doesn't matter if you take the log base b on the outside and b to the on the inside, or if you reverse the order. Let's take another look at that just to kind of get a bit more clarity. So here we have two functions, f of x and f inverse of x. Don't read this as f to the negative 1. It's a poor notation, but it really just means the undoing function for the doing function. So it will undo whatever these operations are. So if we have addition of 2 and we apply that to x, then we get x plus 2. The inverse of adding 2, or the undoing of adding 2, is subtracting 2. We wouldn't subtract 3 to undo adding 2. So the number of the 2 is the same, but we have a different symbol. And so we can actually see that there's a symbol and a number associated with the doing and the undoing. The next basic function is multiplication, and let's just call the operation we want to look at multiplication of 2. If we apply that to x, we have x times 2. Now the opposite of multiplying by 2 is dividing by 2. So again, we have the same number 2 involved, and we have a symbol of multiplying and its inverse symbol of division. When we say something like exponentiation base 2, that means that the x, which is the input of the function, becomes the exponent on the base of 2. And the inverse of exponentiation base 2 is logarithmication base 2. Notice that all of these words end in the sound shun. So function, operation, subtraction, multiplication, exponentiation, and logarithmication. Now again, we have the same 2 involved, but it's really difficult to see the opposite symbol. So I want to really rewrite this 2 to the x using this caret button, which comes from Shift 6 on a keyboard. So instead of 2 to the x, I'm going to write it as 2 caret x. And so this is how you would type it on a keyboard, and this is a computer science notation. So now we can see 2 to the and log base 2 as having the same format. We've got the 2 involved and the opposite operation. So the exponentiation symbol and the log symbol are the inverses of each other. Okay, so now let's take a look at some of the basic properties that we'll be using. We've got change of base, log of a product equals sum of logs, log of a quotient equals difference of logs, and log of a power equals multiple of a log. We're going to look at those in a few examples in just a minute. But let's just look at a few simple calculations. You could pause the video and try these on your own and give a reason, and then you can unpause it and take a look at the answers here. In number 1, it's asking what the value of log base b of the power 1 is. Whenever you see log, think to yourself, what is the exponent on? So what is the exponent that you put on base b to get the power of 1? In other words, base b to what exponent is equal to the power of 1? Well, if we know our exponent laws and our exponent number facts, we know that b to an exponent of 0 is equal to 1, and therefore this value is equal to 0. Because the output of a logarithmic expression is an exponent, and the input of a logarithmic expression is the power. In the next case, what is the exponent on base b to get the power b? In other words, b to what exponent gives me the answer or the power of b? In this case, the exponent is 1. Therefore, log base b of b is equal to 1. In the next case, what is the exponent on base b to get the power in the brackets? In other words, b to what exponent gives us the power, which is called b to the y? Well, here, if we fill the blank or the box with y, we get the answer. And so this is an example of the inverse law, where log base b and b to the cancel. It's not so easy to see this b to the, so if we write it again, log base b of b to the y, we can see now that log base b and b to the are undoing or inverse functions, and we're left with y. That's the same y that we got here. In the next case, b to the log base b of x. So again, instead of writing b and then pushing the exponent up in the air, let's write to the with this caret symbol. So now that all says b to the, and then we apply log base b of x. And so b to the and log base b cancel, leaving us with x. And in other words, we could just say the inverse law for logarithms. That's the same answer for the previous one as well, but you could always rearrange from logarithmic form to exponential form. In other words, we currently have b to some exponent equal to x, and the exponent was all of this log base b of x. And then we can change from exponential form, which says base to an exponent equals a power, which is equivalent to log base of the power equal to the exponent. And therefore we can say log base b of the power, which is called x in this case, equals the exponent, which is everything in the box. And these two statements are true, so we were looking for x here. In the next case, we see that b is the base and 0 represents the power. We know that powers must be positive because we have a table of values from our exponential growth and decay graphs, which must always be positive times positive times positive times positive, and therefore powers can never be 0 or negative. And as a result, we have some strange undefined values here. We can talk a little bit more about those when we talk about vertical asymptotes and non-real results. So a lot of going back and forth between the exponential and the logarithmic form will really help us understand these. Now I want to talk about these next 4 logarithm properties, and I really want to talk about them from the point of view of something we already know, exponent properties, or the exponent laws. So the first property or law is the change of base property, and we're going to use it to evaluate log base 4 of 8. Whenever we want to evaluate a logarithm and we're not really sure what to do, we should introduce an equation so that we can change from log form to exponential form. And so I'm going to let this logarithm equal something, maybe we could call it w. So 4 is my base, w is the exponent, and 8 is the power. So we can rewrite this as 4 to the exponent w is equal to 8. So we want to solve this equation for w because that's the value of the log expression. In order to be good at logarithms, we need to be really good at the number facts that are involved, and so we recognize that 4 and 8 are both perfect powers of 2. And so we can change 4 and 8 to a different base, changing the base. And so I'm going to write 4 as 2 squared and 8 as 2 cubed, and now by our exponent laws we can multiply these exponents together. and then by the one-to-one property that says if one power equals another power and they have the same base, therefore the unique pairing of power and exponents tells us that the exponents must be equal. From here then we get that w must be 3 divided by 2. Now when we think about what this is telling us, we know that 3 is the exponent that we put on the base of 2 to get the power 8. So I'm just going to write exponent on base 2, which implies or yields or gets the power of 8. I'm just using some shorthand notation here because I'm going to run out of room. And then 2 was the exponent that we put on the base 2 to get the power of 4. And we know that we can rewrite the exponent on a base to get a power using a logarithm. So we can rewrite this as log base 2 to get the power 8 in the numerator, and the denominator expression is really log base 2 of 4. Remember, this says the exponent on this base to get that power. And so what we're seeing here is another way of going directly from, well, w, but w is log base 4 of 8. We can go directly from log base 4 of 8 to this thing. Because we have changed 8 and 4 to a base which they have in common, it's easy to say what is the exponent on base 2 to get 8? Well, the answer is 3. And what is the exponent on base 2 to get the power 4? The answer is 2. And therefore log base 4 of 8 is equal to 3 over 2. But we really want to focus on this and generalize that for our change of base logarithm property. In general, we can change the 4 and the 8 and the 2 to any other values as long as they're acceptable bases and powers. So I might say log base a of m is equal to a division of 2 other exponents, because that's what we did. When we solved for the exponents here, we divided the exponent 3 by the exponent 2. And we got w, which was the given expression. So it's a quotient of the exponent that you would put on whatever base you want. Now we put it on base 2 because 2 was something that 4 and 8 had in common. But the exponent that you put on a base to get the power m, which was like 8, divided by the exponent that you put on the same base to get the other power, which was 4. And so this is our change of base formula right here. Okay, so you can take a look at some questions involving that and practice with that understanding. We're going to take a look at the next one, which says log of a product equals sum of logs. In other words, we're taking the logarithm of a product of 2 powers, and that is equivalent to the sum of 2 logarithms. So we're first going to go back to what we know, which is exponent laws. If we have a product of 2 powers, we know that we keep the base and we add the exponents. So we have the product of 2 powers here and here, and we have the sum of the 2 exponents here. This is the exponential version, which we've seen before. This is exponential form, but the logarithmic form says the same information written in a different way. The input here and here, u and v, these are powers. And we see that we are multiplying 2 powers, so we have a product of 2 powers, and we are somehow going to get a sum of 2 exponents. Now the 2 exponents will be the exponent that we put on base b to get the power of u, added to the exponent that we put on base b to get the power of v. So this is just using what we know, the exponential form, to bring in some meaning to what we don't, the logarithmic form. So now the next property of logarithms is that the logarithm of a quotient of 2 powers is equal to the difference of 2 logs, or the difference of 2 exponents. So going back to what we know, exponential form, if we're dividing 2 powers, and remember that a power is a base raised to an exponent, so we have a power divided by a power, and the key thing is that the powers have the same base. We then keep the base and we subtract or find the difference of 2 exponents. So over here, the powers are called u and v, and we're dividing the 2 powers, and we end up getting a difference or a subtraction between the 2 exponents. The exponents are expressed as log base b of the first power, the top power, minus log base b of the bottom power. So again, we're taking what we know, which is exponential form, and we're taking the meaning that's conveyed in here, that we divide 2 powers or subtract 2 logarithms. We turn the exponential form, which is our first language, into our second form, which is our second language, the log form. The last connection between exponent laws and logarithm laws we're going to look at is the law that states that the log of a power is equal to the multiple of a log. Well, we're going to start off with the exponential form that we know. If we have b to the m, which is some power, raised to another exponent, remember b is a base, m is an exponent, so b to the m is a power. If we raise that power to another exponent, we keep the base and we multiply the exponents. Well, in the logarithm rearrangement of that same statement, it says we have the logarithm of p to the n. So p to the n is a power, but p itself is a power because we have the input of a logarithm is a power. This is going to be equal to n times log base b of p. So keep in mind that log base b of p is an exponent, and n was also an exponent on p. So we end up having one exponent multiplied by another exponent, which is exactly what we have over here. Now, I know the letters look a little bit different, and when we prove later on these exponent and logarithm laws, we can see how the letters line up. But really think about what is happening. We're multiplying the two exponents. We're multiplying the two exponents. Now, just to see this in another way, if we took a look at log base b of p times p, we know that that's the same as saying log base b of p squared. But then we can use the sum of two logarithms. So the log of a product is equal to the sum of two logarithms, and we could write this as log base b of p plus log base b of p. And now we have something added to itself, which means that we have two of those things. In other words, if we had a plus a, we would have 2a. And now we have two of these things, so we have 2 log base b of p. And what's really what it looks like here is that the 2 has come down in front here. So we're really looking at the exponential form converted into the log form. Now that we've seen a little bit of an understanding of each of these logarithm properties, and in particular how they relate back to each of the exponent properties or exponent laws, let's play around with some examples. At this point, you could pause the video and then try the examples on your own, or you can watch part of the video until you can see about doing it on your own. I recommend you to do as much of the exercises that follow on your own as possible and use the video as a guide. Okay, well, we have some different logarithm properties and we want to make sure we can go forwards and backwards. Here we have some addition and subtraction and some subtraction with some multiplication. So we need to be using the different logarithm properties. The first one looks like the sum of two logarithms, so you can go back and look it up. Log base b of u plus log base b of v is equal to log base b of u times v. Now, when it was written in the table, in the notes, this was written on the left and this was written on the right. So you have to be flexible about who you put on which side. So in the first case, we have log base 10. Since no base is written, it's an automatic 10, the common base, plus log base 10 of 7. So we keep the base, log base 10, and we multiply the powers of 4 times 7. So we end up getting log of 28. And the next one, we have a quotient. We have a subtraction of two logarithms, and each of these logarithms is an exponent. Rather, the output of the logarithm is an exponent. And so we have 15 is a power, 3 is a power, 10 is the base in each case, and log 15 is exponent, log 3 is exponent. So we know that log base b of u minus log base b of v is equal to log base b of the quotient of the two powers. So we start off with log base 10 of 15, which is an exponent. 15 is the power, but log base 10 of 15 is the exponent, minus another exponent, which is log base 10 of 3. Since the bases are the same, I didn't go and write them all in, but I could do that. Since the bases are the same, we can condense those to a single base, single log base 10, and we divide the powers. Now, whichever has a positive coefficient goes in the numerator, and whichever logarithm has a negative coefficient goes in the denominator. So we end up getting log base 10, or simply log of 15 divided by 3, and we simplify that a bit further to get log base 10 of 5. We can do the next one on the next slide. And so for part C, Before we can do anything with the subtraction, we have to recognize this property that says n times log base b of p is equal to log base b of p to the exponent n. In other words, this exponent comes up on top of the p so that we have p to the exponent n. Just be really careful that you don't write this as log base b of p in brackets all to the exponent of n. So that n only applies to the p and not to all of the logarithm base b of p. Okay, so we're just going to work with the blue property, and we're going to rearrange 2 log base 2 of 6 first. I'll just write it down again. 2 log base 2 of 6 minus log base 2 of 9. So the first thing we do is bring this exponent, or this coefficient, up as an exponent on the 6. So we get log base 2 of 6 squared minus log base 2 of 9. And because these logarithms have the same base, we are able to condense into, or simplify into, a single term, a single logarithm. The next thing I'm going to do is work out 6 squared. So keeping in mind the order of operations, we do 6 squared first and then apply the logarithm to that. This gives us, I'll write over here, log base 2 of 36 minus log base 2 of 9. And now we can keep the log base, and we're subtracting 2 exponents. This is an exponent, and this is an exponent. So anytime we subtract exponents, it is because we were dividing the powers. So we divide the 2 powers of 36 and 9, and we divide them in this order because the log base 2 of 36 has a positive coefficient and the log base 2 of 9 has a minus. So that's the power that goes in the denominator. We keep simplifying and we get log base 2 of 4, and since 4 is a perfect power of 2, we can answer the question, what is the exponent on base 2 to get the power of 4? And we know that 2 to the exponent 2 is equal to 4, so we're looking for the exponent answer of 2. And so we simplify the logarithm as far as we can. So here we want to write this sum and difference of logarithms as a single logarithm. So again, we are condensing. The first thing we notice is that all of the 3 logarithms have the same base, and we have a coefficient here of -3, which we can bring up on the y as an exponent. So there's 2 methods I'm going to show here. The first one is to take just the 3 as an exponent. And when I do that, I can see that I have 2 positive logarithm coefficients and 1 negative logarithm coefficient, which means that I'm going to have the logarithm of a product and a quotient. So I'm going to have 2 powers multiplied together and then divided by another power. Now the power is what we take the logarithm of. So the powers are 5x, x squared, and now the power, it used to be y, but now it's y cubed. And so I can simplify this to be log base 2 of 5x cubed over y cubed. Now the order of operations is that I would work out anything in the fraction first before applying the logarithm. The second method I want to show is what happens if I took the -3 and made that a coefficient, the exponent on y. So here we could see we would still have log base 2 of 5x. We would still have log base 2 of x squared with a positive coefficient. And then as soon as that -3 came up, there'd be a default plus, and that would be plus log base 2 of y to the exponent -3. Of course, I'm running out of room a little bit here, so I'll just move that over. And I'm going to tidy that up because this is actually the key piece that I want to look at here. And so when we have y to the -3, that's the same as 1 over y to the 3. And I'm still running out of room. I'll write that a little bit over. And so instead of the negative in the exponent, I can make that 1 over y cubed. Now each of these logarithms has a positive coefficient, so I'm actually going to multiply all of these powers together. So when I do that, I'm going to get 5x in the power multiplied by x squared in the power multiplied by 1 over y cubed in the power. But the 1 over y cubed means that we're going to multiply fractions straight across and get the same logarithmic expression that we got in blue. 5x times x squared is 5x cubed over y cubed. So whether you take just the 3, like we did in blue, and move it up to the top on the exponent, or you take the -3, you get the same answer both ways. Now, the next piece of this question is to make sure that we are coming up with the restrictions on x and y. And we recognize that the input of each logarithm is a power, and we know that powers must be positive. In fact, this is our domain restriction number 3. So let's just remind ourselves what our domain restrictions are. The first domain restriction is that denominators cannot be 0. The second domain restriction is that radicands of even roots, in other words, the stuff that we take a square root or a fourth root or any even root of, that stuff under the radical, the input, must be greater than or equal to 0. And the third brand new domain restriction is that powers must be positive. Now, the power is only an input for a logarithmic function. So when we have a log function, we have a domain restriction. And so the powers must be positive. I'm actually going to give them all 3 different colors because I want to make sure that all 3 powers are positive and not just one or the other or another. And technically it has to be y and not y cubed, which is the power, because we have to look at the very original statement and not once we have rearranged. So coming up with powers are greater than 0. I'm just going to make this a little bit smaller. We have to have 3 colors and an and in between all of those colors. So to start off, we know that 5x must be positive, and x squared must be positive, and y must be positive. So we can look at these two combined because those are the same variables. And if we plot those on a number line, an x-axis, saying that 5x must be greater than 0, we divide both sides by 5, we get that x must be greater than 0. So to say x must be greater than 0 means a set of x values like this. Now, to say that x squared is greater than 0 means if x is negative and we square it, we get positive. Or if x is positive and we square it, we get positive. The only value that x cannot be is 0, because 0 squared is equal to and not greater than 0. So the green set of values is everything except for 0. And so we're looking for red and green, which is specifically just the right side of 0. So according to this, we only have the set that x must be greater than 0, and we have that y must be greater than 0. So those are the restrictions that we're looking for this logarithm to be true. X is greater than 0 and y is greater than 0. In math, we do a lot of algebra. We do a lot of expanding and factoring forwards and backwards. So here we have a condensed logarithm and we want to work backwards. So we see that we've got the power 4x cubed y squared, and I'm asking to write it as a sum of any two logarithms. So you can take that power, that product of two things, and you can write it, you can write the log of that product as the sum of two individual logs in any way that you want. So we have the same base of 10 for both of our logarithms on the right as on the left, and we can see maybe one of the powers is 4x cubed and then the other power is x squared. There's lots of different variations on the theme, so see if you can come up with some other ones that make sense. Then we want to do the same thing but using the difference and the quotient version of the logarithm property. So instead of seeing this as 4x cubed over y squared, I want to see this as a quotient of two things. Because specifically this was a product of two powers, I want to see a quotient of two powers. So a very simple one would just be to multiply 4x cubed y squared by 1 in the form of anything over itself. You could introduce an a if you like. It doesn't have to be contained with x's and y's. So anything that you have a common factor in the top and the bottom will work. And then we can break this into the logarithm of the numerator power minus the logarithm of the denominator power. So 4ax cubed y squared over a. And of course, there's an infinite number of possibilities here. You should try lots of variations and make sure they make sense. So here we have the change of base formula, which we explored when we looked at log base 4 of 8, and we saw that it ended up being log base, any base, we used base 2 of 8 divided by log base 2 of 4, but we could have used any base we wanted. In fact, let's just take a look on a calculator at log base e of 8 divided by log base e of 4. If you recall, this fraction worked out to be 3 over 2. And now let's just take a look at what happens if we take the natural logarithm of 8 divided by the natural logarithm of 4. So I'm going to set up a fraction here, and I'm going to take the natural logarithm of 8 divided by the natural logarithm of 4, and I end up getting 3 over 2. Now I can take any base, it doesn't have to be base 2 or base e. I could take log base 10 of 8 divided by log base 10 of 4, and I will still get 3 over 2. In fact, I can choose any base I like. I could choose the base of 1035, and I'm going to get 3 over 2. The only bases I can't take are unacceptable bases, bases that are negative, 0, or equal to 1. So we want to make sure that our bases lie between 0 and 1, or greater than 1. So for any base that we have, we can use the change of base formula, as long as the base is acceptable. So let's just write the change of base formula again. If I have log base, say a, of some power m, I can write that as a quotient of 2 logarithms. Now remember that the value of a logarithmic expression is an exponent. So we're really finding the fraction of the exponent that you would put on base 2 to get 8, divided by the exponent that you put on base 2 to get 4. So in this case, I might choose any acceptable base m, and then my top power here is the m, and my bottom power is the a. So we can see that the m is higher than the a, which helps us to remember it. So this is our change of base formula, and we're going to use that to work out log base 8 of 1024. Now, you need to come up with a base that seems to make sense. What base do both 8 and 1024 have in common? If you're not sure, you need to go back to the table of values from the beginning of the unit and make sure you know those number facts. So hopefully you recognize that 8 and 1024 are perfect powers of 2. And now you just need to know which ones. Well, we've seen the bottom one a lot. What is the exponent on base 2 to get the power of 8? The exponent is 3. We saw it over here. And what is the exponent on base 2 to get the power of 1024? Well, that answer is 10. So we get this answer in one step. You could also do it by looking at it from an exponential format. We want to work that out, and to get exponential format out of logarithmic format, you need to make an equation. So if I let this expression be equal to x, now I have an equation. And I know that my base is 8, my power is 1024, and my exponent is x. And I can rewrite this in my native language of base to the exponent equals power. In other words, 8 to the x equals 1024. Now I can change the base from exponential format as opposed to changing the base in logarithmic format. And the base I want to change to is 2. So 8 is 2 cubed, or 2 to the exponent 3, all to the x, and 1024 is 2 to the exponent 10. Now I use my exponent law, which says to multiply the exponents. I keep the base and I get 2 to the 3x is equal to 2 to the 10. Now by the one-to-one property, since I have a power on the left and a power on the right that are equal, and they have the same bases, by the unique one-to-one pairing of one exponent for one power, the exponents of 3x and 10 must be equal. My goal is to solve for x, so I divide both sides, which is where I'm getting a division over here, and I end up dividing the exponent that I put on on base 2 to get 1024 by the exponent that I put on base 2 to get 8. And so it's the same the same answers, the same reasoning, just looking at it from a slightly different perspective. So x, the exponent that I'm looking for, is 10 over 3. So let's just make sure we understand the meaning of this 10 over 3. This is the exponent that we put on the base of 8 to get the power of 1024. And let's just rearrange our logarithmic equation to the more familiar exponential form. Base 8 to the exponent of 10/3 is equal to 1024. And when we have a fraction exponent, we know that the denominator means the type of root that we take of the base. So we're taking the cube root of 8, which is equal to 2, and then we're still raising 2 to the numerator exponent, which is 10. 2 to the 10 is 1024, so we can confirm the understanding of this 10/3. Now let's take a look at part B. If we just remind ourselves of the change of base formula, we have that log base A of m is equal to the quotient of two exponents, or the output of two logarithmic expressions. And we can see that we change the base to any acceptable base, which means a base between 0 and 1 or greater than 1. So in part A, we went from the left side to the right side, but in part B, we have the right-hand format. So if we start off by seeing log base 7 of root 3 is divided by log base 7 of 243, we can condense that into a single logarithm where the base 7 is absorbed or disappears, and we only have the top power and the bottom power numbers. We end up getting log base of the bottom power, 243, of the top power, root 3. Now, if we know our number facts, we see that 243 belongs to the perfect power of 3 sequence, 3, 9, 27, 81, 243, etc. And so this tells us that 3 to the exponent 5 is equal to 243. We can also see that the square root of 3 can be written from radical notation to exponential notation, where the radical means we have a square root, and therefore we have an exponent of 1 and an index of 2, giving us the fraction exponent 1/2. So we may still actually want to rewrite this and to change the base once again from the base 243 to the base of 3, since 243 and the square root of 3 can both be written as powers of 3. In other words, they can be written as a base to an exponent where the base is 3. So I can use the forward version of the change of base formula again to say log base 3 in the top and bottom. And then I have log base 3 of the square root of 3 divided by log base 3 of 243. So what this is really showing us is that we could take any fraction logarithm and we could rewrite this using a different base, any base that we like. In fact, it would be worth going back to the question that we talked about earlier, log base 4 of 8, and remembering that we got an answer of 3 over 2 here. But we were able to change this into a fraction of 2 other logarithms, or a ratio of 2 other logarithms. We used base 2 because 2 was a base that 4 and 8 had in common. But indeed, we can use any other base, like the natural logarithm, which is base e, or we could use base 10, the common logarithm, or any base that we want. And so I'm just going to go to the calculator and show a few versions of different bases to confirm that no matter what base we use, this fraction every time works out to 3 over 2. So let's first consider the expression that we had, which was log base 4 of 8, and confirm that we got 3 over 2. Now let's set this up as a fraction, where we had log base 2 of 8, and that was divided by log base 2 of 4, and we see that we get 3 over 2 again. So let's change this to any base that we like. We could use base 10. We can use base e, and I have to get the value for e here. And of course, another name for log base e is ln, or natural logarithm. So the natural logarithm of 8 divided by the natural logarithm, doesn't let me copy paste, of 4 gives us 3 over 2. And I can use any base that I want. I could use base 1035, as long as the base lies between 0 and 1 or greater than 1. So I'm getting the same answer of 3 over 2, which ultimately is the simpler version of log base 4 of 8. Now, of course, log base 4 of 8, if I just take one more look at it, I could rewrite log base 4 of 8 using a base 4 here and here. And when I do that, the denominator, log base 4 of 4, is just 1. And so we end up getting log base 4 of 8 divided by 1, which is 3 over 2 again. So coming back here, we can answer the question for each individual logarithm. What is the exponent on base 3 to get the square root of 3? Well, the exponent that we put on base 3 to get the square root of 3 is 1/2. And then what is the exponent on base 3 to get the power 243? we put the exponent of 5 on base 3 to get the power of 243. And so we have 1/2 divided by 5, which is the same as 1/2 multiplied by the reciprocal of 5, or 1/5, and our final answer is 1/10. In number 5, we want to take a look at the parent functions and some transformations, and we're specifically asked to come up with a vertical transformation applied to each parent function. So in the first case, we have the parent function is y equals 3 to the x, and then the transformed function is y equals 3 to the x minus 2. Since the minus 2, or subtracting 2, is being done to x before the parent 3 to the function, we can see that the subtracting 2 is a horizontal change, and it's a horizontal translation of positive 2, as we always do the opposite for transformational form. Now, that's not a vertical transformation because it's not being done to y. So we need to really think about our exponent law here and find another way to write 3 to the x minus 2. Well, when we're subtracting the exponents, that meant we were dividing two powers. So we can rewrite 3 to the x minus 2 as 3 to the x divided by 3 to the 2. In other words, y equals 3 to the x divided by 9. Now we can rewrite that equation as 9 times y is equal to 3 to the x. And now we see we have a transformation of multiplication being done to y. So we have a vertical change, and a multiplication is a scaling, and we have this in transformational form, so we do the opposite, and the vertical scale is 1/9. In other words, the graph in red, the transformed graph, is going to be 1/9 as tall, so we're compressing it, but I don't like to use the phrase compression, so we are going to have 1/9 as tall as the original parent graph. So let's try the same kinds of things for parts B and C here. So in part B, we have a logarithmic function, and we start off by writing the parent function, which is y equals log base 2 of x. Now this is the inverse, or the mirror image, of the y equals 2 to the x graph, and it's the mirror image through the y equal to x identity line. So mirror image through y equals x. Okay, so we want to see how this red equation, y equals log base 2 of 8x, is again a vertical transformation. Well, right now we see that the parent function is applied to 8x. So this multiplication is being done to x. So we have a horizontal scale, and we always do the opposite in transformational form. So it's a horizontal scale of 1/8. That's really going to make the graph narrower than the parent graph. But again, we wanted to come up with a vertical transformation. So we need to use our logarithm properties to somehow liberate that 8 from the brackets with the x. And so since here we have the input of a logarithm is a power, and we're multiplying two powers, we can use our logarithmic property to write that as the sum of two exponents. So log base 2 of 8 times x is log base 2 of 8 plus log base 2 of x. Now there's our parent, and we can simplify log base 2 of 8 to be 3. In other words, that 3 is being added to log base 2 of x, after the log base 2 is applied. And therefore, that 3 is being done to y. Well, indeed, it's y minus 3. And since we are subtracting, we know that we have a translation, and it's a translation or a change being done to y, so it's a vertical translation, and we always do the opposite from transformational form, so it's a vertical translation of plus 3. In other words, the red graph is 3 spaces up from the parent blue graph. And let's do the last case in part C. So similar kind of thing. We are going to take a look at the parent graph here, which is y equals the ln of x, which is the inverse of the exponential function with the same base. Remember that ln means ln, or log base e. And so the inverse graph is going to be y equals e to the x. And keep in mind that e is some number, about 2.7, so e lies between 2 and 3. And we saw the exponential graphs of 2 to the x and 3 to the x, and therefore e to the x lies somewhere in between those two graphs. Our red graph that we have given is the transformed version. And so we can use our logarithmic properties to bring that 3 exponent down in front as a coefficient. And so now we have 3 times the ln of x. that 3 is being multiplied by the ln of x, so it's being done to x after the parent function, which means that the 3 is really being done to y. So I'm going to multiply both sides of the equation by 1/3. And since y is being multiplied, we have a vertical scale. And then for transformational form, we always do the opposite. So we have a vertical scale of 3, which means that the graph is going to be 3 times as tall as the original parent graph. In this question, we want to simplify the expression here, and we're going to work from the inside out. So the first thing I'm going to take a look at is the ln of 8 divided by ln of 2, and do some scratch working out. I can change the base, and since I have the powers of 8 and 2, I want to change the base to 2. And so log base 2 of 8 divided by log base 2 of 2 is equal to, well, we could condense that to just log base 2 of 8, just using our change of base formula. And what is the exponent on 2 to get 8? It's equal to 3. Now, you didn't have to do this step. You could have said, what is the exponent on 2 to get 8? It's 3. Divided by, what is the exponent on 2 to get 2? It's 1. And then 3 divided by 1 is just 3. So this first exponent here in the red circle is 3. And I'm going to take a look at this green exponent, log base 4 of the square root of 32. So to simplify this, I know 32 and 4 are both perfect powers of 2. So I'm going to rewrite this using the change of base formula using the base 2. And so the top exponent, the log base 2 of something, has as its power the square root of 32, and then the 4 goes in the denominator. And I'm just going to rewrite this as log base 2 of 32 to the 1/2. And log base 2 of, well, I could write 4 as 2 squared if I wanted to. And then this exponent 2 can come down in front as a coefficient using one of my properties of logarithms. And this 1/2 could come down in front as well. While I'm at it, I could change 32 to something else, 2 to something, or I can simply leave it like this and work it out. So every time I see log, I think, what is the exponent on this base to get that power? And the exponent I put on base 2 to get the power of 32 is 5. So this gives me 1/2 times 5 in the numerator. Similarly, in the denominator, what is the exponent on base 2 to get the power 2? All of that is 1, and 1 times 2 is 2. Or I could have said from here, what is the exponent on 2 to get the power of 4? And that answer is 2. So I have 1/2 times 5 divided by 2. And just be really careful with all of the fractions here. We get 5 over 2 divided by 2, which is the same as 5 over 2 times 1/2, which gives 5 over 4. So the green exponent is 5 over 4, and the red exponent is 3. So if we put all of that into the original expression, I'm going to rewrite the question and almost start it from scratch. So I'm going to say, therefore, 4 to the ln of 8 divided by ln of 2 times 4 to the log base 4 of square root of 32 is equal to 4 cubed times 4 to the 5/4. Now, a couple ways we could do this. We could keep the base and add the exponents, or we could simplify 4 to the 5/4. I know that 5 over 4 is 1 1/4, and so I could rewrite this as 4 cubed times 4 to the 1 plus 1/4, which is really 4 cubed times 4 to the 1 times 4 to the 1/4. Then I can combine those as 4 to the exponent 4, so I keep the base 4 and I add 3 plus 1, and then times 4 to the 1/4, which gives me 4 to the 4, and then this is the 4th root of 4. There are a lot of 4's here. And I might also write 4 to the 4 as one final power, because that's one of the numbers in our table of values. And so if we were to rewrite 4 to the 4, we end up seeing, well, maybe we're not really sure, but 4 to the 4 would be the same as 2 squared to the 4, which would be the same as 2 to the exponent of 8. And if we know that is 256, then we know that 4 to the 4 is 256, and we get 256 times the 4th root of 4. In number 7, we're given some expressions in terms of a base, exponent, and a power, and we're given 2 of those, and we're asked to express the following logarithms in terms of x and y. So what we want to do is recognize that we have a power of 15, and we can break up 15 in terms of the powers 3 and 5 that are given in the information. So for part A, we're going to write this as log base A of 5 times 3, and I'm multiplying 2 powers of 5 and 3, so I can separate that by adding 2 logarithms or adding 2 exponents. And so log base A of 5 is called x, and log base A of 3 is called y. So log base A of 15 is equal to x plus y. Now over here for part B, we have something similar, but we have 125 and we have 9. If we don't know the number facts from the table of values, we won't be able to see how 5 and 3 are related to 125 and 9. So the first thing to notice is that 125 is equal to 5 cubed, and that 9 is equal to 3 squared. So we're going to pull apart those 125 over 9. Since we're dividing these 2 powers, we can write that as a difference of 2 logarithms, or as a difference of 2 exponents. The exponent is the output of the logarithm. And so the numerator logarithm goes in the logarithm, the numerator power of 125 goes with the positive logarithm, and the denominator 9 power goes with the negative logarithm. Then we can rewrite 125 as 5 cubed, and we can rewrite 9 as 3 squared. Then we can use another logarithm property that says that exponent can come down in front as a coefficient for both of those. And we end up getting 3 times log base A of 5 minus 2 times log base A of 3. Now you might say, how did we know to do that? We really wanted to get this expression, log base A of 5, and this expression, log base A of 3. And so what goes in the first red box is x, and what goes in the second red box is y. So we end up getting 3x minus 2y. The next 3 questions are multiple choice questions, and we want to relate the given expression with one of these or not one of these, as the case may be, which of the following is not equivalent. I don't recommend that you do a question like this or just watch the video to get the answer until you're more comfortable with logarithm laws. So you might need to do some practice questions before you attempt this one. So if you don't feel comfortable with the previous questions, move on to some practice questions, some textbook homework, and then come back to these questions later on. So we want to see which of the following is not equivalent to log base 10 of 2. Log base 2 of 10. So I want to rewrite this. There's not a lot to rewrite, so I'm just going to leave that one for now. But I see a quotient here, and I'm going to rewrite log base 2, or log of 2 as log base 10 of 2. And I'm going to rewrite the 1 as a logarithm with the same base. And I know that the power would have to be 10, because the exponent that you put on 10 to get the power 10 is 1. Now I can use the reverse of the change of base logarithm formula, and I can condense this into a single logarithm. It's kind of like that condenses into a single log, and then the denominator power becomes the new base, the numerator power becomes the new power. So I can see that this expression of 1 over log 2 is the same as log base 2 of 10. So that's not the answer we're looking for. Let's do the same thing with part C. We have log base E of 10 divided by log base E of 2. And we saw that we can just change that base to anything else that we want, as long as the base is between 0 and 1 or greater than 1. So in particular, I want to change to base 2. And if I change this to a base 2, my denominator is log base 2 of 2. What is the exponent on 2 to get the power 2? That denominator is equal to 1, so we get log base 2 of 10 divided by 1, which is just log base 2 of 10. So the second one is also equivalent. Here we can do the same thing. We can change base E or base 3 or base 10 to base 2. So if we do that, we get log base 2 of 10 divided by log base 2 of 2. I'm just changing the base to any other base that I like. And then what is the exponent on 2 to get 2? It's 1, and so this is indeed log base 2 of 10. So in this case, it really is a process of elimination that we get log of 5. And this is a tempting answer because somehow we think 10 is higher than the 2, and maybe 10 divided by 2 is 5. But it doesn't work like that. So the answer is A. In the next question, it's again, which of the following is not equivalent to the given statement, log base 10 of x cubed y to the 5. So we can use our different logarithm properties. Here we have the same base in the logarithm of 10, and we're adding two exponents. So we keep the logarithm base, and we end up multiplying the two powers, which gives us x cubed times y to the 5, which is the same. So that one's okay. In the next case, I'm going to put b along here because it'll get a bit crowded. We keep the log base, and then we multiply the two powers. So I'm going to have x squared y to the 4 multiplied by the second power of xy. Again, remember that we have an exponent added to an exponent. And when we're adding two exponents, it meant that we were multiplying the powers. And so if we simplify that, we end up getting log base 10 of x squared times x is x cubed, and y to the 4 times y is y to the 5, so that's the same. In part C, we are going to be subtracting two exponents. So whenever we subtract two exponents, we are dividing the powers. So we're going to have a single logarithm and a division of the two powers. The first power with the positive logarithm coefficient goes in the numerator, and the logarithm with the negative coefficient has its power in the denominator. And so when we keep the log base and we divide the quotients, rather we divide the powers, x to the 4 divided by x is x cubed, and y to the 6 divided by y is y to the 5. And so we end up getting that this is equivalent. Here what we're saying is we have an exponent multiplied by an exponent. And so we don't have a logarithm law for that, and our answer is D. So don't mistake logarithm of the product of a power with the product of two logarithms. That's not what this law says. Now in part 10, we want to find which of the following is equivalent to log base 3 of 11. So a lot of it has to do with changing base. Here we have base 3, here we have base 11, so just apply the change of base formula. And if you need to, you can rewrite it again. Log base a of m, for example, is equal to log base any acceptable base divided by log base any acceptable base, and then the powers are m and a. So you might have to go from left to right or from right to left, depending on what's given. Now, we saw a strategy in the first question where we changed 1 into a logarithm, and I'm going to make the same base of 11 in the top and the bottom. The power in the denominator is 3, and in order to have an exponent of 1 and a base of 11, I need to have a power of 11. Now I can condense that into a single logarithm, and this will condense going from the right back to the left. So the b disappears, the a goes here, and the m goes there. And so I condense this into a single logarithm with the 3 as the base and the 11 as the power. And so that is indeed the same as the first one. So it looks like we found the answer right away, but let's just confirm that the others don't work. So in part B, I'm going to take this -1 coefficient and bring it up as an exponent on the 3. So this is equal to log base 11 of 3 to the -1. In other words, this is log base 11 of 1/3. Now if I wanted to change that to a base of 3, I would need to write it as a quotient of two logarithms with the new base of 3. So currently my base a is 11, and I'm going to change to base 3. And then my power goes in the numerator, and my base becomes the power for the denominator. And I see that I'm not really able to get a single log base 3 out of this. It's just not really working for me. We can get log base 3 of 1/3. We can think of the 1/3 as 3 to the -1. So what is the exponent on 3 to get 3 to the -1? Or, in other words, what is the exponent on 3 to get 1/3? We know that that exponent is -1. So the numerator equals -1 over log base 3 of 11. We're just not getting log base 3 of 11 overall. So this one isn't working. The next case, we have log base 11 of 3, so we could change that to log base 3. In the top and in the bottom, we're going from left to right. And then the 3 becomes the numerator power, and the 11 becomes the denominator power. And here, what is the exponent on 3 to get 3? Well, this is a positive 1, unlike over here. What is the exponent on 3 to get the reciprocal of 3? Was negative 1. And we don't get the same thing. We get the reciprocal of what we started with, which is not the same. So C is not the answer. In part D, we have a base of 3/11, and we want a base of 3. So we do the same change of base formula. Log base 3 in the top and log base 3 in the bottom. And then we put the 11/3 as the power of the top and 3/11 as the power in the bottom. And this really isn't getting us anywhere. So we can be fairly convinced, since we found one already, that it's the correct one. None of these isn't the answer because we found A. There you have a bunch of questions which help you to get deeper into the logarithm laws. The most important thing to remember is that the logarithm laws convey the same information and meaning as the exponent laws. So make sure you're comfortable with the exponent laws, make sure that you know the table of numerical facts, the powers and the squares and the cubes, that will help you get creative, and always go back to talking about base, exponent, power. The best thing to do to get good at the logarithm laws is to practice lots of questions by hand. Good luck!